Last class, we were talking about light. We talked about the electromagnetic radiation. We looked at gamma rays, X-rays, ultraviolet light, that's the one that gives you sunburn. We talked about visible light. We talked about infrared light, microwaves, radio waves, and then I'm going to jump us back to some slides earlier. We learned about the Bohr model, and this is probably a better slide. So we looked at the Bohr model and we said, okay, well, we've got a nucleus in the middle, and that's where our protons and our neutrons are. That's what I was showing us on the previous slide. So all of our big particles, the things that make up the mass or most of the mass, those live in the nucleus. And we've got electrons that can run around on these little cracks, these little tracks. And they start from n equals 1 and they come up. And these orbits have a set distance from the nucleus, and they also have a fixed amount of energy. That spacing gets smaller as n increases. I don't think that comes up particularly much in this class. And one of the ways that atoms can interact with energy is they can absorb energy, and the electrons can get bounced out to a higher energy level. And then after a while, they release that energy. They go back to a lower level. But because energy is conserved, it's neither created nor destroyed, that energy has to go somewhere. And the place that it usually goes is it emits a photon of light, a little packet of light. And the energy of that typically corresponds to a color. It's not always one that we can see. So that was our Bohr model. And we also learned about the quantum mechanical model. And in the quantum mechanical model, we swapped out orbits for orbitals. And so our lowest energy orbital is going to be our n equals 1. N is now our principal quantum number, so our number is our principal quantum number. We added principal in the front. And then we also have a letter that comes after it when we're talking about specific orbitals. And that letter, like S is our first shape letter, and S represents the sphere family. And the sphere family has one object in it, and it's just the sphere. And we have other families or subshells that we can talk about. We've got also different principal quantum numbers. So from 1s to 2s, we're just getting bigger. This is like how in our Bohr model, we had the different tracks. So we go up to a bigger track, we move up to a bigger sphere. There's some other details and intricacies that we're not talking about that you'll learn later if you take Chem 1. When we move on to n equals 2, we can also have the P subshell, the subshell being our shape family, and P stands for peanut. And we can have 3 different shapes in that. We've got 3 different peanuts. We've got the one that's standing up on its end, magical peanut. We've got 2 that are laying down, sleepy peanuts. And they have different shapes and orientations. And when we move on to n equals 3, our third level, or our third principal quantum number level, we get also the D subshell, which we looked at briefly. And in n equals 4, we also pick up the F subshell. And once we're at n equals 4, we don't pick up any other subshells. It's just those 4, S, P, D, and F. And here's what our D orbitals looked like. They're the double dumbbell shapes, except for this one that's got the donut. They bent the second dumbbell around the other one. And this was all sort of just giving us a background, a basis for where are we sticking our electrons. So when we're talking about electron configurations are just where are the electrons, like how many are in each of the different places, the different orbitals. What sort of shapes are they in? We should also know like the shapes behind that, but this was sort of where we were trying to arrive was electron configurations. We also learned about orbital diagrams, the picture version of our electron configurations, where we write in a box and then we put our arrows for electrons up or down. We also learned that orbitals can hold no more than 2, so maxing out at 2 electrons, and they have to have opposite spin. So if we have one up, the other one has to be down. And we did some examples, and then we left off looking at energy levels. This potentially intimidating, scary graph. You don't have to memorize this if you want to for fun for some reason. You can. It goes past 4D and 5S, by the way. There's more levels to it. There's levels to it. But starting off, our lowest energy is going to be our 1s, And then we just kind of move up, and we bounce left and right as we need to. So from 1s, we would move up to 2s, and then 2p comes next. So s comes before p. And then we move on to 3, and we get 3s, and then 3p, and then surprise, 4s, and then 3d. So it's not always necessarily what we would expect. There's some surprises, there's some twists and turns. Keeping in mind, though, that 1s, 2s, 2p, we can do some other electron configurations in orbital diagrams. We're going to do one for carbon. How many electrons does carbon have? Carbon has 6 electrons. It has 6 electrons because it has 6 protons, and the number of protons equals the number of electrons, at least for the neutral compound. So we want to do the electron configuration first. What's our lowest n number? What's the lowest number that we can have? It's 1. What's the lowest or the first letter that we can have? S. So our first number-letter combination is 1s. How many shapes do we have in our S family, our 1s family? It's also one shape, one sphere. And in that one sphere, we can fit 2 electrons. So 1s can hold 2 electrons. We put 2 in. So we initially had 6. We used up 2. So we got 4 left. In our n equals 1, S is the only shape. And so we have to bump up to a higher number. What's the next number after 1? 2 if we're using integers, which we are. So we're moving up to 2. What's our first? Yeah, I was going to say letter, and then my brain stopped working. And we can put 2 into that one as well, because there's also one sphere. And so we had 4 electrons, and now we've used another 2 of them. So we've got 2 left. We're in n equals 2, so we've got 2 shape families. We've got 2 letters that we can access. What's our second letter? The second letter is P. So we're going to write 2P. Who remembers how many shapes we have in our P family, our peanut family? How many peanuts do we have? 3 peanuts. We have odd numbers of shapes. So for S we have 1, for P we have 3, for D we have 5, for F we have 7. It's odd numbers only. I'm sure there's a good reason for it, but that's the way it is. We've got 3 shapes. We can definitely fit 2 electrons into 3 shapes, since we could fit 2 electrons into 1 shape. So we've got some extra room, and we'll see that in the orbital diagram. So we had 2, we used 2, we've got 0 left. You don't have to do the electron bookkeeping along the way. You're welcome to do it like this. You can do it some other way, just as long as we're keeping track. If you can do it in your head, you don't have to write the workout. That's okay with me. All right, so that's our electron configuration. Now we want the box version, the diagram version, the up-down version. And we're going to put in a box for our 1s, because we have one shape, one box. And we had 2 electrons, so we're going up, down. And for our 2s, we're doing the same thing. 2 electrons, 1 shape, 1 box, up, down. And now we get to our 2p group. How many shapes did we have? 3 shapes. 3 shapes. How many boxes? 3 boxes. 1 box for each shape. So each peanut gets its own box. If we were being very robust and detail-oriented, we might label these 2px, 2py, 2pz. We're not going to do that. Yay! But we could do that if we wanted to. We don't want to. And now, this is where Hund's rule, that's here on the bottom. This is our second big rule. Hund's rule. We also had the Pauli exclusion principle. That was our first rule. You can go back and look at that slide if you need to. So for Hund's rule, when we're filling orbitals of equal energy, our 2p orbitals fit that description. See here on this energy diagram, they're all the same level. There's a technical word for that, and I'll tell us that in a minute. So these orbitals are of equal energy. The electrons will fill them singly first with parallel spins. Let me go ahead and box this in for us so we can find it easily later. So what this is telling us is that when we're filling in the 2p with our 2 electrons, we have to fill them in the same direction first until all of those boxes have at least 1 electron, and then they will choose to double up. So we can do up and up. We could do down and down, but we would not be able to do, I'll draw some incorrect examples down here at the bottom. Up and down would be wrong. Another way that we could be wrong would be up and down in the same box. That would also be wrong. Just to give us 2 examples. There's lots of other ways that we can be wrong. I don't think it technically matters which of the 3 boxes you put them into. I usually just go left to right. Any questions or confusions about filling these out? Our fun, I think it's fun word for equal energy, degenerate. I'm not joking. I'm not making that up. That's real. That is, they're degenerate. They're of the same energy level. It's just the way it is. All right, a way that we can think about it that might be helpful, we're going to Mrs. K's chemistry land. Not my chemistry land, Mrs. K's chemistry land. Not my wife, my mother. So in Mrs. K's chemistry land, the Quantum Hotel is where the electrons love to stay. It's a discount resort. The electrons are cheapskates, as it turns out. They will take the first room, the cheapest room that they possibly can. And this is, it's a little bit of a pyramid scheme for the layout of the hotel. So the first floor, we just have 1 room. And the floors count up. We're not British, and so the n equals 1, that's the ground floor, instead of being 1 floor above the ground floor. And then each time that you move up, there's more rooms, up until the 4th, and then it sort of straightens out because it'd be crazy if it just kept getting wider. So we've got just S for our first floor. Our second floor, we've got S and P, because it's gotten a little bigger, because it's an upside-down triangle. It's an upside-down pyramid. And each of these rooms, these are like different levels of accommodations. The S is a single room. There's 1 bed. The P room has, the P room has 3 beds. D rooms are even bigger, deluxe maybe. They have 5 rooms, and F for family maybe 7 beds. The way that the beds work, it's the same way as the beds would work if you and your friends were going to stay and share a hotel room. I assume that this is the way that most people do it, because it's the way that I think most people do it. Let's say that you and your besties go and you stay in a room at a hotel. You're on vacation, maybe spring break. Shout out spring break, we love you. It's coming up. You go and stay in a room. Let's say that there's 3 people. If you and your 2 besties are going to stay in a room that's got 3 beds, what's the arrangement? Are all 3 of you climbing into 1 twin-size bed? No, you probably wouldn't even be comfortable with 2 people in a twin-size bed. The way that you're probably getting into the beds, if I had to guess, since there's 3 beds, one person to each bed. If there's only 2 people, you pick whatever 2 beds you want. Maybe you pick the beds that are furthest apart from each other, because one of you rustles around in your sheets. Rustle, 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 rustle. Right? If there's 3 people. What if there's 4 people? Where does the 4th person go? On the floor? No. Probably not on the floor. The 4th person is going to go upside down in one of the beds. Because in this analogy, the people are not full-grown adults, and they think it's weird if you're sleeping in the same direction. The sleeping with everyone in the same direction, presumably there's a wall behind those beds. It's normal for us to sleep with our heads towards the wall rather than sleeping with your head away from the wall. If you sleep like that. So once you get up to more than the number of beds, then sleep in opposite directions. This would work better if it was like a sleep-away camp and you're in cookie cutters is definitely not the right word. Sleeping bags. Questions? If you don't like this analogy, you don't have to. That's fine. I don't care. It's not mine. It's Mrs. K's. And this is that's what our hotel looks like. It's crazy. Pyramid scheme, for real. All right, so orbital filling order. I mentioned last time, I alluded to the fact that there would be a couple of tools that we could use to remember what order we're filling stuff up. This is one of them. This is one of the ways that you can do it. This requires you to put some stuff down. You might be looking at this and you're thinking, that's crazy. What does any of it mean? Congratulations, you're in the right place. So on the way that we set this up is our N is counting up as we go down. So we've got rows for each of our N numbers. So our 1 is up here, our 2, our 3, our 4, etc. And it's sort of like a grid arrangement. And then along the top, we've got our subshells. So we've got our S, our P, our D, and our F. So we've got columns. And then the way that we cut this the arrows, the path that we're following, are at a diagonal down and to the left. So we're starting in the upper right corner. We cut through our 1S, we cut through our 2S, 2P, 3S, 3P, 4S, 3P, 4P, 5S, 4D, 5P, 6S, and so on and so forth. This will get you the correct energy filling orbital order, which I think is cool. There's a better way to do it, by the way, but I think that this is a cool way of being able to do it. So if you want to remember them this way, you can remember them this way, but we will learn a cooler, easier one that doesn't require you to remember how to put it together. But this will get you, again, the correct orbital filling order. We can also get it from the periodic table, and this is the cooler one. So the periodic table is actually broken into, it's set up with blocks that correspond to each of the subshells. So all the way over here on the left, in our sort of light blue, this is our S block. The S block is just the first two columns. Plus helium. He's included. Sort of like if we threw helium all the way over, this way. We moved it all the way over, then we'd have like a nice clean block. It's all the way on the right side because it's a noble gas, and so we include it in the noble gas group instead. So that's our S block. Next up is the P block with our green here. This is our P block. Stop it. Our P block, I'm accidentally typing periods in searching. So our P block is that far right group. So our first group, S block, first two columns of our main group, last 6 columns of our main group, so excluding our transition metals, is our P block. Anytime that we're in here, what we're filling up is our P block. In the middle is the D block. All of our transition metals are in the D block. And then our F block, wrong order. Our F block is our lanthanides and actinides that get pulled out and set below the rest of the periodic table for convenience, space reasons. So anytime that we would be down here, we would be filling up our F block. Fortunately for us, we're not doing that. So the first part, we have to remember what the blocks are, where they correspond to. The second thing that we need to do is, if we look at the rows, the row / period is the n number with some caveats. So for our main group, our top period is 1. So we're in the S block, we're in 1s. And then what would be after helium? Lithium. Lithium's in row 2. So row 2, we're in which block? S block. So we're in 2s. Once we've finished with lithium, beryllium, once we've moved past that, once we've got 5 or more electrons, we jump over the D block, and we're in the P block. We're still in row 2, and so this whole group, we would be filling up our 2p orbitals. After neon, we would move on to filling up sodium. So this is sort of like if we counted each individual electron that we were adding up. We'd be at row 3. You can go ahead and write numbers in. All right, row 3, we're in the S block, then the P block, then we move on to row 4, where we have the S block, and then for the first time, we hit the D block. What is the n number that our d orbitals show up for the first time? The options are 1, 2, 3, or 4. It's 3. N equals 3 for our first D block. So it's row 4, period 4, but this is our 3 d orbitals because it's our first row of d orbitals. So for our D block, it's n equals row -1. They're all shifted off by 1. So this would be our 3D, and then after that we're in row 4 for our P block, so we're filling up 4P, 5S, 4D, 5P, 6S, and then who knows how the F orbitals work? Somebody does. We won't have to count that far most of the time. I don't invoke F orbitals in this class. So this is the other way that we can figure out the orbital filling order. And there's also some shortcuts that are built into this that are really cool. So this is the way that I would recommend remembering the orbitals. This is going to require you to memorize S block, P block, D block, where row -1 is the number that goes in front. This is the best way to do it, I think. A little bit of a summary. Maybe saying some things that we didn't say already. Lower energy orbitals fill before higher energy orbitals. That actually has a name. Thank you, Germans. The Aufbau, I think it's a principle. You don't need to know that, but you might see it around on the internet. The Aufbau principle. Basically just we're filling up from lowest to highest for energy. Orbitals can hold no more than 2 electrons each. They max out at 2. And they have to have opposite spins. This is our Pauli exclusion principle. And when we have orbitals of identical energy, what's that word? What's the word for identical energy? Degenerate. When those are available, we have to fill these in first singly with parallel spins. For our P's, that's 3 boxes. For D, it's 5 boxes. So we'd have to get 5 with upspin first, and then we could fill in with downspin. So they have to fill in with parallel spins, same direction spins, and then we can fill them in with pairs later for Hund's rule. Let's do some more electron configurations. We're doing them for the sequence of nitrogen, oxygen, fluorine, and neon, and so these are all going to go pretty quick once we've got the first one down. How many electrons does nitrogen have?
7.
Nitrogen has 7 electrons. So nitrogen 7 electrons. I'm going to actually write the electrons on the side. 7 electrons. What's our lowest energy number letter pair? 1s. 1s is the lowest energy. And how many electrons can we fit into 1s? We can fit in 2. So we're going to write 1s, 2. Now we've used up 2. We've got 5 left. What comes after 1s? 2s. 2s comes next. We can also put in 2 there because we've got the one spherical shape, 2 electrons. So now we've used up 4. We've got 3 left. What's after 2s? 2p. And we've got 3 electrons left. We can throw all of those 3 into our 2p. And that would be the full electron configuration. We can also do an orbital diagram. We write a box for each of our things. One box for 1s, up, down. One box for 2s, because s has one shape. Each shape gets its own box. So 2s, up, down. And then 2p, we have 3 shapes, 3 peanuts. We've got 3 electrons, so we go up, up, up. Questions? All right, moving on to the next one. Oxygen, O. Oxygen has 8 electrons. If we look at the periodic table, right, nitrogen. Oh, my laser pointer's dead. I have to recharge those batteries. Is the other one alive? Yay. Oxygen right next to nitrogen. If we wanted to figure out the energy orbitals from just where it is on the periodic table, oxygen is in the second row. We'd have to count through all of the levels first. So we'd go back all the way to the start. This is n equals 1, s block. 1s is full, so we'd max out our s block for 1s. And then up next we would have our 2s. We're past our 2s, so that would be full. And then we're in the p block, so it'd be 2p, and we're in the 1, 2, 3, 4th spot, so 2p, 4. So 1s2, 2s2, 2p4. And then our orbital diagram is going to look very similar. Wow, that looks really similar. And then we're going to add one more in, and that's going to be with a downspin. Because now that we've got 4 people in the room, 3 beds, somebody's got to double up. So we double them up. If we're moving on to fluorine, fluorine has 9 electrons, 1s2, 2s2, 2p. It's in the 5th spot in the p block, 1, 2, 3, 4, 5th spot, 2p, 5. And our our orbital diagram, we would just be adding another down. And then neon would look like this. This is going to be the full n equals 2 principal shell. Because it's at the end, it's at the end of the periodic table. So all of those are going to be our completely full versions. Another thing that I'd like to point out for us, the number of spots. Laser pointer's having trouble. It's old, it's tired. The number of columns or groups that we have in each of the blocks is twice the number of shapes that we have, because that's the number of electrons we can fill in. So for our S, we've got 2 columns. Our S, we just have the 1 sphere shape, and we can put 2 electrons into that 1 sphere shape. P is 6 wide, because we've got 3 orbitals, 3 shapes, and we can put 2 electrons into each of those, so 2 times 3, we get 6. For our D block, it's 10 wide, because we've got 5 shapes, and we can put 2 electrons into each of those. 5 times 2 gives us 10. And our F is 14 wide for 7 times 2. So that'd be enough. If you can remember that, then that's another way we can sort of like work backwards or just use the periodic table to figure stuff out. Now, what if we wanted to do something devious, something evil, something nasty? Not in real life, but like in chemistry. And we wanted the electron configuration for Pb, lead. How many electrons does Pb have? 82. We could do the electron configuration for Pb at 82. It would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. You get the idea. It'd be comically long. Chemists don't like things to be comically long a lot of the time, and so we've got a shortcut. If we're dropping the E from mole to shorten it to mole, you better believe that we're putting in an abbreviation system. And so the abbreviation system, the electron configuration of the previous noble gas, can be abbreviated, yay, by the symbol for the noble gas in brackets. Symbols being things like He, Ne, etc. in brackets. So if we're looking at sodium, sodium's Na. What's the previous noble gas? Ne. So we just go up 1 row all the way to the end column, the last group, 18 or 8A. Ne, neon, is our previous noble gas. It's just the one on the previous row. So for sodium, neon is the previous noble gas. I don't know what I was doing there. That's going to be the symbol Ne. So the way that we use our shortcut, sodium has 11 electrons. Our shortcut for the electron configuration is going to be Ne in brackets. That takes care of everything up until the row that we're in. How many electrons does neon have? It's got 10. Neon has 10 electrons. We had 11 to start. We used up 10 with our shortcut. We've got 1 electron left to place. What row is sodium in? 3S. It's in the 3rd row. It's in the S block. So our next thing to fill up is 3S. We have 1 electron. We can put that 1 electron into the 3S. The other way we can figure out the 1 is it's the first spot in the S block, so it's 3S1. 3rd row, S block, first spot, 3S1. That's like the fastest way to do it, I think. The fastest way to do it. This is very nice. It saves us a lot of time, especially the further down you get in terms of like rows. Your turn. Write the electron configurations for each of these elements. We'll go over it together in a couple minutes. A couple minutes have passed. We want to do electron configurations for our elements. First one we're looking at is aluminum, so we're looking at the 3rd row, the far left side of our second part of our main group. Aluminum is not in the first row. So we can go back to the previous noble gas, which is going to be neon, Ne. So we've got neon, put in brackets. We love a shortcut. So starting from neon, the next element is sodium. Sodium is in row 3. And what block is that in? S. So next step would be 3s. Are we past the S block? Yes, we're past the S block. There's 2 spots in the S block, so that would be 3s2, where it's full. Then we jump across to aluminum, and aluminum is now in what block? P. It's still in the 3rd row, so 3p, it's in the first spot, 3p1. Electron configuration. If you do it this way, you only have to count, you don't have to do any math. Counting sort of math, but you don't have to like subtract number of electrons or anything, which I think is nice. It's faster, even if you're really good at math. Next up, bromine. Bromine is in the 4th row, so its previous noble gas is the one in the 3rd row, which is Ar, argon. So we're putting the symbol Ar in brackets. If we wanted to do the math version, we can do that. So bromine has 35 electrons because it has 35 protons. Argon has 18 electrons. So when we're using our argon shortcut, we're subtracting 18 electrons. That means we would have 17 left. What row is bromine in? What row? 4? And what's the first block that we encounter in row 4? It's the S. So 4s. How many electrons can we put into the S? We can put 2 in. We put 2. Take off another 2 electrons from our 17. We've got 15 electrons left. After potassium and calcium, our row 4 S block, we run into scandium. And scandium is in what block? D. What's the number going to be? It's going to be 3, because it's our first encounter with the D block. N-1, or row -1, gives us our N number of 3. D shows up for the first time in N equals 3. So 3D. How many shapes do we have in D? How many orbitals? 5 orbitals. 5 orbitals, 2 electrons each. How many electrons can we put into 3D? We can put in 10. So subtracting 10, we've got 5 electrons left. After we've made it through, we ran through the whole 3D block. Now we're in what? P block. And we're in row 4, 4p. P has 3 orbitals, 3 shapes, 3 peanuts. We can fit 6 electrons in it, so we can easily place our 5 remaining electrons. And now all of our electrons have been placed. So that would be the way if you're doing the math along the way. That might be something like what it looks like. You'd have to remember the number of orbitals, the number of shapes. You'd have to remember to do all your subtraction. You'd have to do the subtraction. That would get it. Otherwise, you just count across. And that would also work. And then last but not least, we have SR, strontium. Strontium's previous noble gas is krypton, Kr. After Kr, we've got what row? 1, 2, 3, 4, 5. And we're in the S block, so 5s. Which spot in the S block are we? First spot or second spot? Second spot. So 5s, 2. Second spot, 2 electrons. Questions about any of those? Cool, and then we're going to skip this because we already did an orbital diagram for carbon. I don't know why it's in there. It's because I haven't taken it out, is why. All right. Building. Stacking concepts on top of each other. We're on a hot streak of stacking concepts on top of each other. This is going to continue for a while. We've got a whopping 146 slides in this chapter. We're on slide 50. So we're about a third of the way through this chapter, which is crazy work. We're going to continue stacking concepts for like the entire chapter, and we will continue to use this and build off of this later as well. So the part of the reason that I'm saying this is to stress the importance of making sure that you are caught up on where we are, that you sort of have some understanding at least of what we're doing currently, so that when we move on to the next thing, you're not completely hopelessly lost. If you are completely hopelessly lost, you can go to Logan's SI sessions. That would be a great place to go. You can also go visit our STEM ambassadors in the STEAM room. So part of the reason we're talking about electron configurations is so that we can talk about valence electrons. Valence electrons are outside electrons, outermost electrons. So if we remember back to our Bohr model, right, where we had the orbits, the tracks where the electrons travel on, our valence electrons are the ones that are on the outside track. On the highest n number / track. Those are our valence electrons. For our quantum mechanical theory, these are the ones with the highest principal quantum number n. The reason that these electrons are important is because they're on the outside, they're the most easily accessible electrons, so they can engage in bonding. They can be transferred between different things. They can also be shared in the form of bonds with different things. Electrons that are not in the outermost principal shell are called core electrons. Everything under the highest n is core electrons. And we can apply this to our electron configurations. So silicon has this electron configuration, 1s2, 2s2, 2p6, 3s2, 3p2. It has 4 valence electrons because 3 is the highest n number that we have. And then everything else is core electrons. We've got 2 plus 2 plus 6 gives us 10 electrons. If we were using our shortcut, neon in brackets, then this represents 10 core electrons. We can also have other core electrons if, for example, they show up in our d orbitals. D orbitals are always going to be core electrons. Any questions before we stop? Then we stop.